Our next speaker is Gabriel Cuomo, who's going to talk about conformal collider physics at finite.
Okay, so thanks a lot. Thanks a lot to the organizers for this wonderful workshop. So this is going to be about some work that, what was the kind of work here? Oh, yeah. With these three gentlemen, Aaron Pirat, who's at the side of moving to Cambridge, Filippo Nardi, who's also student at TFL, Lorenzo Ricci, who's a postdoc from Maryland, and please check out the closely related works that appeared before ours by Chicherin, Kolcheski, Sokashev, and Boyadov, and also the work by Matt Walters with Ricardo, Sasha, and okay, so I'll start with some introduction, then I'll have some brief review of the EFT I'll use, and then I'll talk about the main part. Okay, so I think you had yesterday a wonderful talk about detectors. I don't think I have to introduce them too much. Natural Lorentzian observables in QFT are either S-matrix elements, we all studied since our early days in QFT, but well, also since the 70s, we know that actually there are other observables in a very natural class is to just insert a detector in between your initial and final states and measure basically fluxes of energy and other properties of your final state. These are not really distinguished morally because really when we measure exclusive final states, so our cross-section, we are really measuring infinitely many detectors. That's how we distinguish the particles. They're not really distinct things. But the nice thing about this set of observables that is being realized since the 70s is that they're defined and also calculable importantly, even when this matrix is not. So for instance, if I start with proton-proton collisions in QCD, these are infrared and collinear state observables, and we can also talk about them in CFT if I define a property of the initial state. So I don't want to spend too much time on this slide. In particular physics have many uses. Yesterday we had a wonderful talk about this. But roughly the idea that how you define these detectors is that you choose an angle in your celestial sphere, and you wait for the flux of whatever collision happened to appear here. So this is roughly the formula of the energy detector, which is the most used, most studied detector. And it's well known since the 70s and has been revised by Hoffman and Maldacena that these detectors emit natural OPs when the two angles come close by. And this OP is associated with the standard collinear splitting that we studied again in perturbation theory. So in CFT, things simplify a bit because in CFT, matter travels at the speed of light. So I can just move my integration contour directly to lie on null infinity. So this is a picture of the Minkowski diagram in 2+1 dimension. And what you should imagine that you have some bunch of matter here, you make it evolve, and then eventually we hit the detector. So we have detectors are naturally defined. They are more general, but a very simple class consists in just integrating operators, local operator with some spin in the null direction, x plus and x minus here are null direction at angle n. And the energy detector just follows then from this formula, which is the limit basically of the formula I showed before in CFT. Okay. So an important fact is that in CFT, these are special instances of light ray transforms. So they are definite transformation property under the conformal group. This means that, for instance, a detector is nothing but a light ray operator at infinity. So it has a certain scale dimension, which is given by the inverse of the spin, 1 minus j, and a certain spin, which is 1 minus delta in terms of the delta and j of these operators. Okay. And there are various applications, most importantly in the context of Frege conformal theory. Okay, so the motivation for this talk is very simple. So there are many available results for detectors observable in few particles of Barton states like E plus E minus, or in the case of CFT, light CFT operator. For instance, the Wilson-Fisher fixed point, people studied detectors in single and few particle states. But there is like, okay, in standard LHC collision, we kind of know what to measure already. Well, been doing this for ages, so it's very useful there. But a natural place where detectors may be the only available option is to study phases of matter that are actually non-trivial states, so not just few particle states. And that is being proposed, I think, starting in this paper, that energy correlators, for instance, would be a natural probe of quark-gluon plasma in a ion collision. So, okay, I will not really go to phenomenology here, but this kind of motivates studying the interplay of these very relativistic observables in very non-relativistic states that are described by non-relativistic effective field theories. And as many of you know, I worked a lot on a certain class of non-relativistic EFT, so this was my natural starting point, but I'm currently working on generalizing. But the starting point in this talk is going to be event shapes. Event shapes are just expectation values, several detectors in a certain incoming state. in large charge CFT states. So there. Okay, so let me review quickly the effective field theory. Okay, so I want to study, I guess, all this motivation led us to study, well, led first Matt and collaborators, and then us to study detectors in states created by large charge operators in CFT. So the idea is that there is state operator map, so a state with large charge and zero angular momentum will naturally correspond to states with an operator with large charge and zero angular momentum will naturally correspond to a state with large charge on the cylinder. So this is a state with finite charge density, roughly Q over R squared, where R is the radius of the cylinder, sorry, Q over RD minus 1, so it's a typo here. And this means it's a state with large chemical potential compared to the geometric scale. So this is a condensed matter state, and then we should ask what kind of state this is, so that we can describe it. There are two natural options. If you just look at nature and if you don't tune anything, you find either metals or Fermi liquids, or you find condensation, find superfluids. So there are two natural options to consider also in CFT, that this state is either described by a Fermi surface or by a superfluid, and they are formally distinguished by the fact whether there is the U1 symmetry spontaneously broken or unbroken. Here, assuming that the global symmetry of the CFT is a U1. And in many cases, like your two model in 3 dimensions, we know that the right answer is the superfluid, so I'll focus on this class, but many of the things I'll say you can repeat them in this case. So let's assume that we have a CFT, say the O2 model in 3 dimensions, and let's assume that we want to describe large charge states in this CFT. So we want to describe it through an effective field theory, and the natural effective field theory is the superfluid EFT. Basically, this follows because of a spontaneously broken U1 symmetry. So this means that you will broke the U1, and the Hamiltonian is just a dilation to a diagonal combination. So there is a Goldstone mode that appears in a linear combination with a chemical potential like this. And generically, there can be other modes, but they are expectedly gapped, and they are gapped by the largest scale that can appear, which is the chemical potential scale. So under the assumption that no accidental light modes occur, I can write everything in a derivative expansion in powers 1 over mu, which means powers 1 over the charge. Yeah, I forgot here to cite Hellerman and collaborators. So this is the effective field theory. People have done this exercise for you. And the leading order is just d chi to the d. So this is d mu chi to some non-analytic power, but remember that chi is mu t plus pi. So this is actually analytic in the equation. And then you have some leading correction that scale with inverse powers of the charge compared to the leading term, and so forth. So the most famous application of the CFT is that you can predict scaling dimension of large charge operators. So the lowest dimension operator of fixed charge is actually dimension scales like qd over d minus 1 plus corrections. And these corrections have been calculated, and in fact, these coefficients are related to these C's and have been measured on the lattice for the O2 model in several theories. And again, I think here I'm giving credit to the people who first came up with this construction in 2015. Okay. So I also can quantize the theory. Quantize the theory just means I expand into fluctuations. So I have even the cylinder. So I have integral over time and integral over the angular coordinates, and then this is my fluctuation Lagrangian quadratic coordinate. It's very simple. It's just a phonon mode with speed of sound 1 over d minus 1 because I'm in a conformal setting. And then from here I extract the dispersion relation of this pi, which is just given by this formula. So this is just the eigenvalue of the Laplacian on the sphere, and this is d minus 1 is the speed of sound. Just notice that if I plug L equal 1 in this formula, then I get omega 1 equal 1. So this means that the first angular momentum mode of this perturbation creates the standards of the CFT primary. So that's consistent with conformal invariance. And okay, for this talk, I care that I can also compute correlation functions. I just have to compute the stress tensor of my theory, for instance, and then use the propagator of this Goldstone mode. Roughly what you find is something like this. You have a leading order, which is the classical expectation value. So the theory is semi-classical, it's nothing surprising. You have a classical expectation value. And then you have propagators that now normally appears with derivatives. So, and here I'm just schematically writing it. You have an expansion in 1 over q or 1 over delta q. Q, remember, goes like qd over d minus 1, so it's large. And the propagator is nothing but an expansion basically into the state that you exchange in this channel. So you see an exponential corresponding to the energies of the phonons that appear. Okay, and then here you have a Gegenbauer because you're on the sphere, so you don't have momentum, you have angular momentum, and that's why you have Gegenbauer's polynomial. Okay, and this, okay, this you have to do an exercise to compute this factor. Of course, this is a CFT, so this is related. This expectation value on the cylinder is related to a 4-point function. Something that will come up later, so let me spend like a few more seconds on this, is that this 4-point function is a mixed Euclidean Lorentzian 4-point function if I don't do smart analytic computation. So this is because the state on the sphere is created by inserting the primary operator at minus infinite Euclidean time. Okay, so you see here I have Lorentzian observable, here I have something inserted in Euclid. So I guess those will, many of you are educated in radial quantization, so it might be obvious, but let me spell it out anyhow. So the reason why you need this projection to minus infinity is that an insertion of a conformal primary at a random point will create the primary and the descendants, all of them together. And I want to project onto the ground state. So to project onto the ground state, I just go to very far away in the Euclidean path. And then if I multiply by the appropriate factor, I will be left with the lowest energy state, and the rest will be exponentially suppressed. So that's the state operator map spelled on the cylinder. Okay. So this is the review of DFT, and I think there are no questions started there with that part. Okay, so now we learned how to do EFT.
Why things break down?
Why things break down in default 2? Well, I mean, it's not like the EFT breaks down, but generically in default 2, we have Moody symmetries, and you can show that unless the central charge is 1, in which case the EFT is exact, it's just a compact boson, then the EFT doesn't possess these Moody symmetries once you account for corrections. So it's not that it breaks down, but the rational CFTs are not described by this EFT because it doesn't have the right symmetries.
There's no chance that
A non-rational CFT could be described by this, but we don't know examples, so people have not looked too much into this. Okay, so detectors in effect. Okay. I introduced the state, I introduced the detectors. Now what I want to compute is just expectation values of this detector in these states. Okay, so what you do is you insert operators of Q at some point X and the conjugates of point X. These are all Whiteman functions, so ordering is as it appears, and the Fourier transform. And this is, I'll call this as the expectation value of K detectors. So here I'm focusing on energy correlators, but I'll talk about more general ones. So the picture you should have in mind is that I'm inserting a bunch of charge at some point around the origin in my Minkowski diagram, and then I let it evolve, and it will naturally evolve in concentric shells at the speed of light until it reaches null infinity. That's just by conformal invariance. So I want to measure the flux that my detectors hit here. Okay. So here, obviously, what is interesting, the 1-point function is trivial, it's fixed by conformal invariance, it's been known for a while. What is interesting is higher point functions in CFTs, and so in particular, 2 or higher point functions. And as anticipated, I'm interested in the universal dynamics of this 2-point function in the limit of large charge. Okay, so why is this exercise worthwhile talking about? Okay, you might say, why are you even talking about this? It's straightforward. You compute your expectation value on the cylinder. I already computed it for you. I analytically continue the insertion from Euclidean to Lorentzian space, and then map to flat space the result. That's what you do in CFT. And then you compute your integrals. Okay, so if our exercise had been this, I don't think I would be talking about this. But in practice, there are 2 reasons why it's worth discussing it at least in a short talk. First is because there are technical challenges. So this program of analytically continuing the insertion mapping to flat space is very technically challenging because we don't have a closed form expression basically for the Goldstone propagator. We just have it as a sum. And in particular, there are several orderings of the operator that appear in this integral. So you have to worry about a lot of subtleties. So given the simplicity of the FT, this doesn't sound the right approach. And the other thing is that, which is more conceptual I hope to talk about, is that these light rate integrals span regions where the effective field theory breaks down. So this is actually technologically interesting. We want to learn the interplay of these detectors with effective field theory. We want to understand how to incorporate the breakdown of EFT where it happens. Let me just explain briefly why you should expect this. Because you see, you have some charge here, it evolves until null infinity, but it's going to evolve in concentric shells. And you can roughly imagine it's going to be localized roughly around here if you start from the origin. But you're integrating over the full null infinity. So close to spatial infinity and future infinity, the flux will be very diluted. And if the flux is very diluted, you should expect hydrodynamics expansion to break down because hydro works when the flux is large. So this is an intuitive reason, and we will be more precise in a moment. So our strategy will be not to do this procedure, but will be to first Fourier transform. I'll show you why this is convenient, and then do a map of this calculation directly to the cylinder where the effective field theory is obvious. Okay, so let me explain the main technical part of the talk. So the basic observation is that the 4-point function or n-point function you're interested in factorizes basically in the 2-point function of the heavy operator and some expectation value, whose main property is that it doesn't depend exponentially on the scaling dimension delta Q and therefore on the charge. But okay, so now at this point, you see there is something which is exponential and something which is sub-exponential. What do? When you do an integral, you do saddle point. So, and then what pleasantly happens, and kind of intuitively nice, that once you do the Fourier transform by saddle point of something which exponentially depends like this, you are projecting your operators, your operator insertion to complex time. So the saddle point is complex. That's actually the main trick we use. And the complex position is precisely given by this. This is already nice because I told you that what we like is mixed Euclidean Lorentzian correlator. So this already starts to look like that. This is a simple exercise. And of course, this is systematic in that I can compute correction to the saddle point by expanding, and the expansion just amounts at expanding these operators around this complex insertion. You can do this in terms of insertion of conformal generators. So there is nothing new I need to compute. Okay, so now I arrived at this formula here. This is easy. Now at this point, all I have to do is to invent a nice map between this formula and the cylinder EFT. And the map is well known. The map, in fact, this I don't need this complex insertion, is that I can embed my Minkowski diagram into a triangle inside the Lorentzian cylinder. This is, of course, well known. This is the explicit formula, but it's not too important. It's just a Weil map. What is, however, important and follows from the Fourier transform is that once I do this map, these complex insertions map to infinite Euclidean time on the cylinder, and therefore just map to my ground state operator. So this is precisely what I like to compute, or what this is to compute. Okay. So in the end, after you do all this mumbo jumbo and the smoke's clear, you arrive at a very simple result where your detector expectation value you care maps to some cylinder expectation value that now you know very well how to compute with some factors up front that follows from conformal invariance. So the cylinder detectors on the cylinder, they clearly lie on the null infinity, which maps just to a finite line of the cylinder. This is another simplification. And you just do the Weil map, and if in terms of like coordinates on the cylinder, they are written in this way. So this is, again, this is well known, but the interesting thing is that they map to the right state. Okay, so now the exercise, the most technical part of the exercise is done. We can discuss some physics. Okay, so I reduce my problem to finite integrals in the cylinder FTLI. Okay, the leading order is obvious. In fact, you didn't need, it was already studied by math, and you didn't need all this discussion. And it's basically the idea that the expectation value of the stress tensor in the large charge operator factorized into a classical term plus correction. And it immediately follows that the leading order result is a factorized result for the detectors as well. So in particular, there will be an expansion in 1 over delta Q, and the leading term will be just classical expectation value. I think Kyle mentioned this yesterday. And in this case, as I told you, the 1-point function is fixed. So this proves already some sort of universality. It should be clear from what I said. All I used here is that the operator was heavy and there was some classical physics here. So this is a universal prediction for every state. It has been emphasized in this paper. But it's also a bit unsettling because we would like to find some non-trivial result. And for this, we need to go to the next order. So the next order is slightly more interesting, but less universal at the same time. So here I'm using, here you will see the dynamics of the EFT. So the next order is basically given by 2 terms. The first is the correction to the Fourier transform that I told you I did by saddle point, but they have correction to the saddle. I can compute them, and this gives me this term. This is boring. This is equal in free theory and interaction theory. And the next term is that and the other term, which is interesting, arises just integrating the connected part of the correlation function, the cylinder, which is roughly what I showed you before. Some derivative of some propagator suppressed by 1 over delta Q compared to the leading order. Okay. So now, how do we do this calculation? So the first thing to notice is that you know that this propagator has some short distance singularity, because I didn't write it down, but it's obvious it's a field propagator. So when the two fields come close together, there is a singularity because a massless field has a singular propagator. And then you can, by using this, you can compare this term, the integral of this term with the leading order, and ask when does my FT breaks down. And you find that the FT breaks down when the angle between the two detectors is of order of the inverse cutoff, Q minus 1 over D minus 1. That's my cutoff. So that's roughly what you expect. And you know that this should have been the case because in the very collinear regime, you have the collinear OP of the detector that's not part of the FT, it's part of the CFT data. So that should have happened. And it follows by this analysis. Another technicality that I don't want to discuss is that to integrate at arbitrary angles this Green's function in practice is still not straightforward. You several, you need to some alternative decomposition of those that Green function I showed. And so let me just say the physics here. The physics is that here, these two detectors, they are everywhere space-time separated. So it means they're everywhere also outside the sound cone. So this means that you're describing the exchange of an off-shell quanta between the two detectors. So this is a potential. The potential should decay with some power of the distance, but the propagator decomposition I showed to you is just amounts of quantizing in this channel. You just see something that oscillates in time. So that's just a physical rephrasing of the technical statement. The conformal block decomposition doesn't converge in absolute sense for these observables. Luckily here, we have control over the theory, and we can write new decomposition that make manifest the property that this propagator really corresponds to some potential exchange that has some definite long distance behavior and short distance behavior that we can characterize. It's still a numerical calculation, but let's just say it takes some care. Okay, this is technical, but in the end we get a result. Okay, here I'm just showing it for energy detectors in equal free, but we can do it for any detectors. So this is the result for the first correction divided the two one-point functions. So there is the disconnected piece, which is these dashed lines, and the connected piece, which is these blue dots. So we have to sum the two, but we separated them in this plot. And the angle here is the angle between the two detectors, is theta. So the disconnected piece is pretty boring up to now, but the connected piece is more interesting. Let me just note that the dots are numerical, but the red and green lines are analytical approximation, the small and large angle limit where we have some control. The most interesting feature is that you see some of a singularity. That wasn't noted. There is no obvious collinear effect in the CFT, but still there is a singularity that comes from the fact that the phonon propagator is getting enhanced at short distances. And this is somewhat analogous to the QCD jets, so where we see singularities at small angles. So we were led to dub this as a ground jet because this is a jet induced by the phonon. It's negative, so this truly means since this object has to integrate to a constant by word identities, the fact that this is negative truly means that you have some large amount of correlation stored here at t equals 0. And this is not crazy. This always happens with these objects. There are distributions. So they have normally contribution which are stored at 0 angle. And in fact, we even computed this contribution and it perfectly accounts for the word identity. So again, this is completely analogous to the calculation in QCD jets. Okay. So this is the main physics result. Let me just, so I think I have one last slide, which I wanted to show. So this is a slightly more technical point, but I think it can be useful, or I suspect can be more useful, so I wanted to show it. So I told you that there is some breakdown of perturbative theory at some point. So we want to characterize this breakdown. So from the viewpoint of the cylinder, the breakdown, which was associated to some infrared effect, flux dilution, because of the miracles of conformal invariance, becomes associated to a short distance effect. So here I depicted for you the two contours of the light ray on the sphere, and you see that they touch at the initial point and at the final point. So there you have short distance effect that you need to characterize in your detectors. So this means that if you want that, strictly speaking, naive FT breaks down here. But of course, we are educated effective theorists, so when things break down, we just add new terms. So the way my claim is that the way to treat this contribution is to claim that your detector, that in UV they were just integrals of operators that you could control, in the EFT maps to the effective field theory detectors, because I can just map my operators from the UV to the infrared. But then I have new contribution that account for these singularities that I call matching counterterms. And the beautiful thing, okay, at this stage, this formula is not very useful, is that these matching counterterms are completely constrained by the conformal properties of the Dirichlet operators. So I can just tell you that, okay, this formula is going to be a bit technical. It basically depends on this position and these two angles. This position is these two endpoints. Okay, you read this complicated formula. This is fixed by conformal invariance. But right away, without doing any calculation, I can just estimate by matching this in the EFT that the contribution of this region, which is outside of EFT, will scale very suppressed in Q. So the scaling depends on the operators I consider. For such a scalar operator, it's actually very important. But let's say for the energy correlator, it turned out to be very subleading. But I want to stress that this approach is completely systematic, and you can check it against some cutoff approach. And it's very nice because I think it works. I suspect this can be a useful lesson also away from this simple game we played today. Okay, so let me just summarize. I'm out of time. So basically, okay, what I told you is that we have a systematic effective field theory approach to study detectors in these large charge states and hopefully more general heavy states. And we presented some explicit NLO results. There are several official directions. I think in light of the physics motivation, it would be very nice to study heavy and thermal states in CFT. That's what we're thinking about. This should be described not by superfluids, but by fluids. And here the analogy with the phenomenology gets a bit closer, so that's why it's interesting for us. There's a more conceptual question. I showed you some results in EFT, but eventually these results in EFT have to match to OP, to the collinear OP, which is fixed by completely different physics. So one would like to study this transition, and one needs some weakly coupled model to do that, or some holography. And of course, optimistic, and this I hope to learn also from the audience. Can we learn any lessons for maybe AVI in physics, or can I learn from anybody in the audience any lesson for AVI in physics in a way that can be useful? Because yeah, been struggling to understand the literature. But yeah, and with this, I thank you.
More questions for Gabriel?
Yeah.
It's kind of a little bit my analogical. You are talking about, say, EFT and the available expression. Available expression is kind of you talk kind of division by distance, right? So short distances, like in expression, and then matrix element will take. And when you're saying EFT, no, the implication of what we are doing, right? I'm trying to understand if there is a separation of scale.
Yeah. So when the OP holds, the FT breaks down, and when the FT holds, the OP is not useful. So like they are really orthogonal. So in this plot here, at some point, the behavior at very small angle order 1 over cutoff, so 1 over some point of the chart, will behave and will be dictated by the OP. But this I cannot compute within effective field theory. But this was one of the questions.
Yeah, no, but okay. Say in the paper expression you're introducing, say, for example, normalization point, right? You're dividing момент by larger and small. When you're saying this EFT, it's in this way, it's not short distances, right? It's not like a direct expansion. Because what you are observing, it certainly includes large distances, right?
Yes.
And then, I mean, if I'm trying to introduce analog of normalization point, how we divide, this replication of EFT.
I'm not sure I understand.
Okay. So EFT means that it's still division, right? That something is
sure.
included. In a perturbative, what is included is short gradient distances, right?
Yes.
What is included in the EFT?
I mean, here it's like higher. It's like here I'm just going large. Well, I think even there is not real relativity, but large time and spatial distances separately they work. Yeah, so you don't need
So a division in time or?
But I think both, you need some, both of them, well, naively would like, well, as long as one of them is sufficiently large, there is no light-constant singularity in FT, right? Because it's phonon, there is no any more light-like particles. So as long as the objects are separated either in space or in time, then you would say that you can do CFT. And yeah.
Okay,
And
because for me it's kind of a little bit of confusion,
yeah,
between the, what's it called, what is a B and what is a T, because I used to see certain variable equation as effective C as well, right? It also.
yeah, okay, I see what you're saying. Yeah, but I mean, what I'm saying is that the OPE, okay, here it's not clear. There is a subset between UV and AR because we're in CFT, but OPE is determined by CFT data that are not just Wilson coefficient effective theory. So you need more information than the FT clearly. So it was more of a consistency check that we cannot reach the OPE regime once we do the estimate. I guess it was X factor. But it's a bit confusing from the viewpoint of Minkowski because this OP is associated to collinear and infrared singularities, not UV one. The miracle of CFT that infrared is the same as UV in a sense. So here it becomes so clear.
Thank you.
Right, in the interest of time, I suggest that we continue discussions over the coffee break, and since we are running a little late, let's meet again at 10:50, right? And now let's thank Gabriel one more time.